Welcome to Theory of Computation. This is lecture number 39. What we did in the last lecture was we started looking at the theory of p-space completeness. The theory of p-space completeness is just like the theory of NP completeness, except for now we're looking at even harder problems. These are problems that belong to p-space and everything in p-space is reducible to them. As we saw in the theory of NP completeness, that once we defined what NP completeness, it was not obvious at all if there exist problems which are NP complete. In fact, the existence of NP complete problems is a central theorem in complexity theory, the Cook-Levin theorem, which told us that satisfiability is NP complete. But what we did in the last lecture was actually define what does it mean for a language to be p-space complete. The definition was simple enough. Remember, that language has to be itself in p-space, and the second thing is that every language in p-space must be polynomial time reducible to it. Then we sort of looked at why is it that we're using polynomial time reducibility. The answer was, well, we want the reducibility to be easy. One of the consequences of this definition was that if any problem in p-space turns out to be in P, then the class p-space will be equal to P. Therefore, p-space complete problems are the hardest problems in the whole class p-space. In fact, in some sense, they are problems which represent the whole complexity of this class p-space. One more thing that we noticed was that p-space complete problems must also be NP hard problems. All p-space complete problems are also NP hard. Therefore, they are at least as hard as NP complete problems, and it's widely believed and suspected that they're even harder. That it's probably extremely unlikely that any p-space complete problem can be solved in polynomial time. Once we have the definition of p-space completeness, well, the first thing to do is to prove that there is at least one p-space complete problem. Remember when we did this with NP completeness, that was a central theorem. That was the Cook-Levin theorem. The Cook-Levin theorem told us that satisfiability is NP complete. It identified a concrete problem from Boolean logic, and this concrete problem from Boolean logic turned out to be NP complete. That gave us one NP complete problem, and we use this problem and reducibilities to actually prove that a host of problems are NP complete. What we want to do now with p-space completeness is something similar. We want to identify one p-space complete problem. Well, what kind of problem would that be? It's not obvious how to search for p-space complete problems, and of course, the theorem which will show us that there exists a p-space complete problem is going to be an ingenious and wonderful theorem, just like the Cook-Levin theorem. Nevertheless, what we did was we started looking at a generalization of satisfiability. A generalization of satisfiability comes from looking at fully quantified Boolean formulas, which we'll call as quantified Boolean formulas for short. Quantified Boolean formulas are formulas which have quantifiers for all and there exist, and all the variables in the formula are quantified. Since all the variables in the formula are quantified, therefore, these formulas must be either true or false. Therefore, sometimes we call these sentences. And in this case, our universe is the Boolean universe. Thus, every variable can either take the value true or false. So, telling whether a fully quantified Boolean formula becomes a computational question. Or in other words, if we collect the encodings of all fully quantified Boolean formulas which are true, that becomes a non-trivial language. And this is the quantified Boolean formula problem. And what we want to do today is to prove that this problem is p-space complete. In order to do that, we'll have to first prove that this problem is in the class p-space. So I will have to convince you that there's a polynomial space algorithm which can analyze a fully quantified Boolean formula and eventually tell you whether it is true or not, and it would only use polynomial space. And the second thing I need to do is to prove to you that all languages in p-space are reducible to this TQBF or true QBF, and this would establish that this language is p-space complete. So in today's lecture, what we're going to do is look at the definition of TQBF, this language, or we will precisely say what the computational question is. Then we will prove that TQBF is p-space complete, and after that we may talk a little bit more about some other p-space complete problems. So let's begin today's lecture. Let's start by looking at what a fully quantified Boolean formulas were and how do we define them to be true or false. Let's look at an example that we started with last time. We had a formula phi which was for all x there exists y, x or y, and not of x or not of y. So this is a fully quantified Boolean formula because there are two variables in it. It's implicitly understood that both these variables are Boolean variables, and both these variables are quantified. X is quantified using a universal quantifier for all, and y is quantified using an existential quantifier that exists. Once we have this formula, what we can do is we can come up with a formula which is only on one variable. We do this by throwing away the first quantifier and the variable that goes along with it, and substituting in the formula for that variable the value 0, and that gives us our first formula, which we call phi restricted to x equals 0. So in this case the formula is there exists y, 0 or y, and 0 bar or y bar. The other formula we can get is by setting x equals 1 and throwing away, of course, the first quantifier. So in this case, phi restricted to x equals 1 is there exists y, 1 or y, and 1 bar or y bar. So if you have a fully quantified Boolean formula on n variables, you can get two formulas. One will be by taking the first variable, throwing its quantifier away, and in the formula substituting every occurrence of that variable by 0, and in the other case by 1. You get these two formulas, and the number of variables now goes down by 1. So every n variable Boolean formula, quantified Boolean formula, gives rise naturally to two formulas which are on n-1 variables, which are defined there for you. Now what we do is we define for all x1 phi to be true if phi of x1 equals 0 and phi restricted to x1 equals 1, if both these formulas are true. Well, recall, so this way we define the truth of a Boolean formula on n variable to be true based on whether these n Boolean formulas on n-1 variables are true or not. Of course, this is an inductive definition. And how do we tell if a Boolean formula, a quantified Boolean formula on 0 variables is true? Well, it doesn't have any quantifiers, and it's just a formula over constant zeros and ones, and it's made by connectives ands, ors, and nots, and we simply evaluate the formula to find out its truth value, and in this case and, or, and not are given the usual interpretation. So we're coming up with an inductive definition. Similarly, we define there exists x1 phi to be true if either phi restricted to x1 equals 0 is true or phi restricted to x1 equals 1 is true. These are very natural definitions, and they are the same definitions that we've gone through, but now our universe is Boolean variables. So this is how we define a Boolean, quantified Boolean formula to be true. Let's look at a quantified Boolean formula and find out whether it's true or not by following this definition, or let's at least start the process so that this concept becomes clearer to you. Let's work out a concrete example. Let's consider the formula that we considered before, which is for all x there exists y, x or y, and not of x or not of y. In this case, we can obtain our two formulas. Phi restricted to x equals 0 is there exists 0 or y and 0 bar or y bar. And phi restricted to x equals 1 is there exists y, 1 or y, and 1 bar or y bar. And both of these formulas must be true for the original formula to be true. So originally we had a formula with two variables, two quantified variables. What we did was we created two formulas on one variable. And since the original variable that we substituted was universally quantified, therefore both these one variable formulas must be true for the original formula to be true. So let's find out if these formulas on one variable are true or not. Next, now we want to check if there exists y, 0 or y, and 0 bar or y bar is true. For this, we have to check if the following two formulas, if one of the following two formulas must be true. The first formula is obtained by substituting y equals 0, and that formula is 0 or 0 and 0 bar or 0 bar, which evaluates to false. This means we need to check the other formula as well, which is phi restricted to x equals 0 and y equals 1, which is the formula 0 or 1 and 0 bar or 1 bar. And this evaluates to true. So this tells us that phi restricted to x equals 0 is true. So what we have found out is that one of the formulas, phi restricted to x equals 0, is true. Now for phi to be true, the other formula, phi restricted to x equals 1, must be true because x was universally quantified. It was, the formula started as for all x. Well, you can check once again following this procedure whether phi restricted to x equals 1 is also true. And if that happens to be true, then the original formula would be true. If that's false, then the original formula would be false. And you can follow this process and figure out whether phi is a true formula, true fully quantified Boolean formula, or whether it's a false fully quantified Boolean formula. So we recall that we were considering originally phi, and we made these two formulas. And both these formulas must be true for the original one to be true. We've checked the first one now, and now the second one needs to be checked, which you can do yourself and figure out whether the original formula is true or not. Now, this procedure, if you think about it, is a recursive procedure. And this recursive procedure leads itself to a recursive algorithm. So, the procedure with which we check if a Boolean formula is true or not, which is given to us by the very definition, becomes a recursive algorithm. What we can do is write down this recursive algorithm and ask the question, how much space does it take? We would ask the space question since we are now studying space complexity. So let's first look at this algorithm. So we're given a definition of when a QBF is true, and this definition leads us to the following recursive algorithm. It's going to evaluate whether a formula is true or not, and therefore I've called it eval phi comma n, and n is the number of variables in phi. If n is equal to 0, then phi has no variables. It is just made out of constants with the connectives and, or, and not, and we can directly evaluate and return its value, and that value would be either true or false. So this is the base case or the terminating case of our algorithm. When the quantified Boolean formula has no variables, it's just a formula over constants, the algorithm simply evaluates its value and returns that. what happens if it has some number of quantified variables? So if n is greater than 1, then x1, let it be the first quantified variable in phi. Then phi can be one of these two formulas, or it can be a formula in one of these two forms. It would either be if the form says there exists x1 followed by psi, or it would be of the form for all x1 followed by psi. If it's of the form there exists x1 psi, then we produce the first formula, evaluate it, then we recursively evaluate it and produce the second formula and recursively evaluate it and use the boolean connective to return the right value. So in algorithmic terms, we return eval of phi restricted to x equals 0, comma n minus 1, or phi restricted to eval of phi restricted to x1 equals 1, comma n minus 1. And this is what we do in the first case. So we're just simply following the definition. In the second case, if phi is equal to for all x1 psi, we return the evaluate of phi restricted to x1 equals 0, comma n minus 1, and eval of phi restricted to x1 of 1, comma n minus 1. So this algorithm is simply following the definition. It is a recursive algorithm, and so we have to compute its space complexity. Well, to look at a recursive algorithm, to look at the space complexity of the recursive algorithm, the first question you should ask is, how deep is the recursion? How large will the stack grow? Because recursive algorithms are implemented using a stack. So the first thing to notice is that the depth of recursion in this algorithm is only n, where n is the number of variables. Because every time a recursive call is made, n is decremented by 1. And once n reaches 0, it hits the terminal case. Thus, the stack will have depth n. The other thing you have to ask is, well, how much space is used by this algorithm and how much space is put on the stack? So, we are not going to go into very nitty-gritty details, but the only thing we'll convince ourselves of is only polynomial amount of space is needed, or only polynomial amount of local variables need to be pushed on the stack for this algorithm to work. So for example, if you look at this algorithm, all we need to do is just push the current phi on the stack and then compute phi restricted to x equals 0 and evaluate it. And when the call returns, we can pop the stack and then compute phi restricted to x equals 1 and make the recursive call. Thus, at any point of time, only you need to store one formula on the stack, and that has polynomial length. Therefore, this is a polynomial space algorithm. The space complexity of this algorithm is polynomial in the length of the input, and therefore this algorithm runs in polynomial space. This shows that TQBF can be solved in polynomial space, because how do you solve TQBF? You simply take the input, which is the formula phi, and call eval on it. If eval returns true, you accept, otherwise you reject. So you simply evaluate the quantified Boolean formula using the definition recursively in order to come up with a polynomial space algorithm. Next, our goal is to show that TQBF is p-space hard. This is not going to be easy, because we have to show that for every language A in p-space, A is polynomial time reducible to TQBF. So, showing the p-space hardness of the first language is going to be difficult. This is the same thing like the Cook-Levin theorem. It was an extremely general theorem. Similarly, we'll have to prove an extremely general theorem, namely that any language A in p-space is polynomial time reducible to TQBF. Let us start. Well, what we have to do is take an arbitrary language A in p-space, we do not know much about A. The only thing that we know is that it belongs to P space. This means that there is a Turing machine M that accepts A and uses polynomial space. Let us take this Turing machine M and collect a few facts about it. So, just like the proof of Cook-Levin theorem, how did we prove Cook-Levin theorem? We had to prove that every language in NP is reducible to SAT. So we said, okay, if A is a language in NP, then there's a non-deterministic polynomial time Turing machine. Let's look at this Turing machine, and we collected a few facts about it. Similarly, now we have A, which we know is in P space. And so what we do is, we know that there is a Turing machine M which requires polynomial space and accepts this language. So first, let's collect some simple facts about this Turing machine. The first thing we know is that this Turing machine takes polynomial space. So every configuration of this Turing machine would be of polynomial length in the length of the input. That's one thing we know. So first we observe that the machine runs in space order n to the k. Therefore, it accepts in time at most 2 to the order n to the k. Well, this thing that we know, we are given that this algorithm or this Turing machine M runs in polynomial space. But from there we can conclude that this algorithm runs in time 2 to the order n to the k. And that was something that we discussed earlier. This you can prove by using counting. 2 to the order n to the k is the total number of configurations that you can make in space n to the k. Therefore, since this algorithm always halts, it cannot repeat any configuration because it's a deterministic algorithm and it would be going into an endless loop. Thus, this algorithm must halt in time 2 to the order n to the k. So we can not only every polynomial space bounded algorithm has a time bound. This time bound is 2 to the polynomial. So it's not a very good bound, but yet we can bound how much time does this algorithm or does this Turing machine take. And this is going to be useful. So let's collect this fact. Let's go further. Now suppose X is an input and C0 is the initial configuration of M on X. What we know that is M accepts X if and only if an accepting configuration of M is reachable from C0 in at most 2 to the order nk steps. So what we are saying is, if M accepts X, it must accept it in this much time. We have an upper bound on the time. Well, if it accepts it in that much time, then from the initial configuration to the final configuration, it must reach in that many steps. So this is a simple thing we are saying. What does it mean for M to accept X? Well, M accepts X, remember, if and only if X is an A. And we were doing similar things with the Cook-Levin theorem. Lastly, we can also say that M accepts X if and only if there is an accepting history of M on X of this length. So, in other words, we're doing something which is extremely similar to the Cook-Levin theorem. Can we use the same ideas that we used in the Cook-Levin theorem in order to prove this theorem? Remember, we're going to come up with a quantified Boolean formula which is going to be true if and only if M accepts X. So, by looking at this input X, we want to create a quantified Boolean formula which is true if and only if the Turing machine M accepts X, which is the same thing as X being an element of A, and this would be our polynomial time reducibility. So, what we want to use is the same ideas as the ones that we used in Cook-Levin theorem. In the Cook-Levin theorem, each configuration was of polynomial length, and the length of the computation history was also polynomial. So, in the Cook-Levin theorem, every configuration had polynomial length, and the total number of configurations were also polynomial. However, in this case, every configuration has polynomial length, but the total number of configurations is huge. It's 2 to the polynomial. So we can try to use the same ideas, but this would not give us a polynomial time reducibilities. We need to do something more. We need to look at the proof of Cook-Levin theorem and use some additional ideas in it. Thus, what we're trying to do is the following. Let's look at it in detail and see what exactly we're trying to do. We know that M accepts X if and only if there's an accepting history of M on X of length at most 2 to the order n to the k. Now we'll try to construct a quantified Boolean formula phi sub M of X such that phi sub M of X is true if and only if M accepts X. Furthermore, and this is the bulk of the proof, the formula will have polynomial length and would be computable in polynomial time. So the trick here is that the computation history is exponential. It's 2 to the order n to the k, 2 to the polynomial. Yet we want to come up with a polynomial size formula which captures the notion whether M accepts X or not, whether such an accepting history exists or not. And this is going to be an extremely short formula, and this formula is going to talk about an accepting history which is extremely long. So we would need additional ideas more than the ones that we used in Cook-Levin theorem. Let's go ahead and see how we proceed. Firstly, we know from the proof of Cook-Levin theorem that we can encode configurations in Boolean variables. Remember, in the proof of Cook-Levin theorem, we had a configuration and we took Boolean variables. And we said that we could write down a formula which would be true if and only if these Boolean variables, the settings of these Boolean variables, correspond to having a configuration. Let us use this as a black box. We could make a formula on variables x, and the only thing we need to know is that x had polynomial number of variables in the length of the configuration such that this formula con of x is true if and only if the assignment of variables of x corresponds to a configuration. So in the Cook-Levin theorem, we saw a one-to-one correspondence between Boolean variables and configurations. In other words, we could talk about configurations in the language of Boolean variables. We will use that as a black box in our theorem. Thus, we will refer to configurations with a bit of reminders instead of referring to Boolean variables. Strictly speaking, when we are talking about configurations, we're talking about the underlying Boolean variables that represent this configuration. Now, recall that suppose we are given two configurations C1 and C2. So we're given a configuration C1, a configuration of this Turing machine, and we're given another configuration C2 of this Turing machine. So this configuration was represented by some variables, a set of variables x1, and the other configuration is represented by some set of variables x2. What we could do was make this very special Boolean formula. And this Boolean formula that I'm going to call yields y sub m, m denotes the Turing machine that we're talking about, x1 comma x2, it is going to be true if and only if C1 yields C2 in one step. So what we can do is we can express the fact that a configuration yields another configuration via the rules of the Turing machine using Boolean logic. This was the heart of the Cook-Levin theorem, and we're using this as a black box. So this way, what we can do is we can use Boolean variables, Boolean logic to say that a configuration yields another configuration using the rules of this Turing machine. And if you remember, this was a critical part in the Cook-Levin theorem, and this is where we use the ideas of windows of size 6. So maybe you want to go back and look at the proof of Cook-Levin theorem if you want to understand the details of this proof completely. Now, we could also make a formula which checked if a configuration was accepting. That is, given a configuration C with corresponding variables x, we could make a formula accept x, which was true if and only if C was an accepting configuration. So, in other words, Boolean logic allowed us to check if a configuration was accepting as long as the configuration is represented by a set of Boolean variables. This also came from Cook-Levin theorem. There was something more in the Cook-Levin theorem. Lastly, given an input X and a configuration C with the corresponding variables set X, we could make a formula initial M comma X, which was true if and only if C was the initial configuration of M on X. So this was another formula which we created from the Cook-Levin theorem, and once again we are using it as a black box. Now what did we do? We simply put these ideas together. Our last formula in the Cook-Levin theorem was simply saying, does there exist a configuration C0 all the way up to Cm such that each Ci is a valid configuration, C0 is the initial configuration of M on X, Ci yields Ci plus 1, and Cm is an accepting configuration. And the Cook-Levin proof told us how to do each part. We ANDed all of this together, and then we said, is this formula satisfiable? If the formula was satisfiable if and only if they existed C0 up to Cm with these properties. But if they existed, that meant that the machine M accepted the input X. So we would want to do something similar for this proof of p-space completeness also. What if we do exactly the same? What would go wrong? Well, in this case, M has to be 2 to the order n to the k. This is very large and not a polynomial. So this is not going to work. If you say, does there exist C0, C1, C2, all the way up to C2 to the order n to the k, that's just too long of a formula that you would create. You would need too many variables. It's more than polynomial. It's 2 to the polynomial, order polynomial. Therefore, this is not going to work. You will get a reducibility. It would be an exponential time reducibility, not a polynomial time reducibility. So this is not going to work. And now what we're going to do is use something called the folding trick. We'll fold up this formula. This trick is going to be similar to the trick that we have used in the proof of Savage's theorem. Let's look at it. Recall that we have the quantifiers for all and there exists. And we did not have both these quantifiers before, or in satisfiability, the only quantifier allowed is there exists. So now we have this additional quantifier, so why not we use of it? Let's make a formula y c sub 1 comma c sub 2 comma k, which is true if and only if C1 yields C2 in at most k steps. So remember our previous formula yields y sub m of C1, C2. That was telling if C1 yields C2 in one step. Now we're going to make a more complicated formula which has a parameter k in it. And it would tell us if the configuration C1 yields C2 in at most k steps. So if we set k equals to 1000, then y C1 C2 1000 will be true if and only if from the configuration C1 you can go into configuration C2 using 1000 steps of the algorithm or of the Turing machine. So this is going to be a more general formula. Let's see how we can make it. Well, how would we make y of C1 comma C2 0? How will we express the fact that C1 yields C2 in 0 steps? That's very simple. A configuration yields another configuration in 0 steps if and only if configuration 1 is equal to the configuration 2. Thus, what we can do is insist that all the variables corresponding to the first configuration are equal to the corresponding variables of the second configuration, and this can be simply put in Boolean logic. The second thing was y of C1 comma C2 comma 1. How do we make this? Well, this was the heart of the Cook-Levin theorem. that's where we learned how to express that C1 yields C2 in at most one step. The Cook-Levin theorem taught us how to do that. Now, using these two, how can we make y of C1, C2, k? Let's look at it. Well, all that we have to observe is y of C1, C2, k is true if and only if there exists a C prime such that y of C1, C prime, k over 2 is true, and y of C prime, C2, k over 2 is true. Why is this the case? Let's discuss this. What is this thing? It says, the first part says I can yield C1 from C2 in k steps. The second formula says, well, there's an intermediate state that there's an intermediate configuration so that I can go from C1 to the intermediate configuration in k over 2 steps, and then I can go from that intermediate configuration to C2 in k over 2 steps. This is just like the reachability problem. We said that a vertex S was reachable. From S we can reach to T in k steps if and only if there's an intermediate vertex where we can reach in k over 2 steps, and then from the k over 2, then again using k over 2 steps we can reach our final destination. Similarly, in this case we're saying from the first configuration to the second configuration we can go in k steps if and only if there's an intermediate configuration so that the first configuration to the intermediate one we can go in k over 2 steps, and from the intermediate configuration to the destination configuration we can go into k over 2 steps. So now let's stare at this. We realize that in making this formula this way, we're using only the quantifier that exists, and we're using the boolean connective and therefore this gives us a recursive way of making this formula C, y, C1, C2, k. So we can use recursively this trick to make this formula, and at the end of the recursion we will have to make y of C1, C2, 0, which we know how to do, or y of C1, C2, 1, which Cook-Levin taught us how to do. So now we can make this formula, and so this is a very nice way of making this yields formula, and now it has a parameter k, and this parameter k tells us how many steps we are allowing the machine to take to go from C1 to C2. So we've been able to make this formula, but let's not rejoice. What we need to do is find out how long this formula was, because remember, if we use directly the proof of Cook-Levin theorem, we do get a formula. It's exponentially long and it's not a polynomial time reducibility. And the problem is the formula is so wrong that even if we write it down, it would take us exponential time. So let's see how long will this formula be. Let's say that the length of each of these formulas, y C1, C2, 0 and y C1, C2, 1 is r. Then what would be the length of y C1, C2, k, which is written as there exists C prime y C1, C prime, k over 2 and y C prime, C2, k over 2. What would be its length? Well, if you look at this formula, which is, so look at the parameter k. When I want to make a yields formula with parameter k, I have to take two yields formulas with parameter k over 2 and put them together. And then I have to connect them with a boolean connective. Not only I have to connect them with a boolean connective, then I have to also put some quantifiers and a configuration here, which is going to be a set of variables. Nevertheless, let's see how much it all would take. Let's compute the length L sub k. Now this L sub k is, we can write down a recursion for this L sub k under these assumptions. What we have is L naught is r. That's what we have assumed, that initially these things are r, or when we write down k equals 0, these are r, and L1 is r. And then we have the recursion L of k is equal to 2 times L of k over 2 plus, let's say, order 1. Of course, to write down a configuration that does not that requires more than order 1. So I'm doing a very conservative analysis. This is going to be a lower bound on the length of the formula that I would get. Well, what happens if I try to solve a recursion like that? Let's even, instead of order 1, just put a 1 there. Or let's not even put a 1 there, just leave it out. So the length of the formula is, so a formula parameterized by k is made out of two formulas parameterized by k over 2, which is made, each one of them are made out of two formulas each, which are parameterized by k over 4. And each 4 of them are made out of two formulas each, which are parameterized by k over 8. This is a very simple recursion. Any computer scientist can solve it. If you solve this recursion, or if you lower bound this recursion, it's very easy to see that what you're going to get is L of k is going to be greater than or equal to r times k. So L of k is going to be r times k at least. Now this is no good, because what we wanted was, we want to use this yields formula for a very large value of k. In our case, k is going to be 2 to the order n to the k. So we need a new idea. So this way of recursively building up this formula didn't quite work. We weren't able to reduce the length. And the reason we weren't able to reduce the length is because if you were trying to make a formula for k equals 20, you had to take a formula for k equals 10 and another formula for k equals 10 and put it together. And therefore, the length wasn't really reducing, or the length of the formula was becoming more and more. What we would want to do is compactify this formula. Let's try to do it in a more clever way. If you look at our definition that we have given below, so the formula, the yields formula is given below to you, we have not used the quantified for all at all. Remember, we are dealing with fully quantified Boolean formulas, and they have the quantifier for all also. We've not used it at all. And we've not used it in this recursion at all. Somehow, if we can make use of a for all and make the recursive less expensive, we'd be able to go home, in the sense that we'll be able to do what we want. So all this thing we've done is we've left out one very important ingredient which is given to us in these quantified Boolean formulas, that is the universal quantifier. Now it turns out we can use this universal quantifier to compactify this thing and to fold this formula and make it shorter. So let's look at the new definition. Let's consider this formula, which is much more complicated, but let's read it. So we're saying that we can yield from C1 the configuration C2 in k steps if there exists a C prime such that for all pairs C comma D in this set, we can yield C from CD in k over 2 steps. Now what is this set? This set has two pairs in it. The first pair is C1 comma C prime, and the second pair is C prime comma C2. So let's look at the first pair and see what would it give us if we substitute that pair for C comma D. It will give us C1 comma C prime. And if we substitute the second pair, it will give us C prime comma C2. Therefore, this formula would be equivalent to there exists C y of C1 comma C prime comma k over 2 and y of C prime comma C2 or k over 2. Therefore, this is a new way of writing down the old formula, and we have used the quantifier for all. But that's not what's important. What is important is, let's stare at the first formula again. If you look at the first formula, y c comma d comma k over 2 only appears there once. It does not appear there twice. Therefore, it's not that the formula that is parameterized by k is made out of two formulas that are parameterized by k over 2. it's made out of only one formula that is parameterized by k over 2. Plus there's some additional stuff. Now this additional stuff is there exists C prime for all C comma D in this pair. So that additional stuff is of length polynomial if all these configurations are of length polynomial. Nevertheless, the formula that comes afterwards, y of C comma D k over 2, is not repeated, and this compactifies the length. Let's calculate the length. In this case, once again, we assume, and in this case now, we just assume for simplicity first, that the length of y c1 comma c2 comma 0 and the length of y c1 comma c2 comma 1 is r. Then what would be the length of this new formula that we have written? Let's compute the length L sub k. The length L sub k of y of c1 comma c2 comma k will be given by, once again, a recursion. It would be L0 is r and L1 is r, that's given to us, and L of k is equal to L of k over 2 plus order r. So what we need to do is now try to solve this recursion. If we are able to solve this recursion, this would tell us how long our formula would be. Thus, if we solve this recursion, we realize that L of k is order r log k at most. And if k is 2 to the order n to the k and r is polynomial in length, then this whole thing becomes polynomial in length. Once we have done this, the proof of the reducibility becomes almost trivial. Now here is the point to understand. Remember that order r log k, in this expression, k doesn't appear itself in there, but only its log appears there. And log of 2 to the order n to the k is going to be n to the k. Or log of 2 to the any polynomial is going to become a polynomial. Thus, using this for all quantifiers or universal quantifier, we've been able to cut down the length of the formula that we produced drastically. And using this trick, now we can come up with our reducibility. If we now look at the following thing, now suppose we are given x and we construct the formula y ci comma cf comma 2 to the order n to the k and initial mci and except mcf. This is going to be a quantified boolean formula, and this is going to have polynomial length. Furthermore, this formula is going to be true if and only if m accepts the input x, and this would be a reduction from a to qbf. And the length of this formula is going to be polynomial, and we will be able to compute this formula in polynomial time also. Thus, what we are going to do is use both the quantifiers that exist in for all to fold these formulas so that they have polynomial length. Once we have done that, our reducibility is going to be trivial. In the next lecture, we'll see how the details of this are done, and then after that, we will start looking at some other very interesting p-space complete problems. P-space completeness is a very nice theory. We'll see that this QBF turns out to be p-space complete, but many combinatorial games that you play at home like chess, are also, you can define versions of them that turn out to be p-space complete. So many combinatorial games are p-space complete. An exciting game that I told you about was Generalized Geography, which is p-space complete. So let me tell you what that game is, and you can think about it and see if you can come up with a version of it which you can then prove is p-space complete. Generalized Geography is a game which is played between two teams, and first team, or geography, let's not talk about Generalized Geography, but let's talk about geography first. It's a game that is played between two teams. The first team says a name of a place, a city or a continent or a town or a province or a region in the world. And the other team, so they say a name of a place, let's say Karachi, and the other team now has to say another place, but the rule is that the region that they talk about or the city that they talk about or they say must start with the same letter that the last one ended on. So if the first team says Karachi, then the second team can say Islamabad, but they cannot say Rawalpindi because Rawalpindi does not start with the same letter that Karachi ends on. You continue this game and you're not allowed to repeat any of the cities that have already been talked about. And the team that is not able to find a new city under this rule, the first team that is unable to do that loses. A version of this game called Generalized Geography is P-Space Complete. We'll see that in the next lecture. Till then, thank you and goodbye.